Also, after every in class, you're gonna find under grades, you're gonna find, for example, in class assignment 0, you should get a grade. I didn't post it yet, I'll post it after this lecture. But in case someone who attended the in class and got, for example, a 0 out of 10, everyone who attended gonna get a 10. But whoever attended and got 0, that means it's a mistake from my side. So you email me or tell me in the next day, for example, and I will update it for you. So you can check your grades like day to day. Any questions? Okay. So let me start with today's class, which is normal and shear stresses. So I don't know if you remember the example that I said before, that force doesn't indicate intensity, stress does. But let me explain it a little bit deep. I spoke about the example that if I wear a heels or a shoes and I stepped on your hand, it's different. Actually, this is not something it was in my mind. It was like an example in a book. And it's not like as violent as I explain it, but I got it from here. So if, for example, I'm going through the same example again, and like let's discuss why wearing heels is more intense than like if I wear shoes and I stepped on your hands. So, for example, if I weigh 200 pounds and I stepped on your hand, and I had two options. Either I wear a heel with a tip of a diameter of 0.4 inches, and I wear a shoes with like 8.6 inches times 2.7 inches. You all agree that wearing a heel will hurt your hands more than wearing a shoes, right? That is why when we speak about intensity, we speak about in terms of stress. And how is the stress distributed over an area? So if the same load is distributed over a smaller area, that will be more intense. Let's see why. So this is something we call stress. And stress, there's a lot of stresses that we explain in the lecture now, but all the stresses has the same equation, which is the force over area. And it's your job to see which area that we are talking about in all these stresses. So in this example, I will say, okay, the stress, and we call it sigma. This is the symbol for stress, for actually normal stress. We call it sigma, and it's force over area. So let's see now if the 200 pounds, that's my weight, over the area of the heel. So I'm wearing the heels now, and I stepped on your hand. So the diameter of the heels, which is pi d squared over 4, which is 0.125 squared over 4. And it's because I assume this is like a circle. And the area of a circle, you have two options. You either say pi r squared or pi d squared over 4. Either pi times radius squared or pi times diameter squared over 4. So we said that intensity is measured by stress. How much force is distributed over a unit area, which is inch by inch or inch square. So the stress here is going to be 1,600 pound, which is this, over inch square, which is the diameter of the area of like the circular heel. So now you find that every inch square in your hand gonna feel 1,600 pounds per inch square. Let's compare it now if I wear a shoe and I stepped on your hand. So it's gonna be 200 pounds over the area here is 23.22, and it's gonna be 8-ish. Yeah, 8.6 pound square inch. So wearing a shoe, each inch square in your hand gonna feel 8.6 pounds. And if I wear a heel, each inch square gonna feel 1,600, which tells you that that's why you're gonna get hurt if I stepped on your hand with a heel on. Out of curiosity, I just like Googled, in order to breach or pierce human skin, you need at least 100 pounds per inch square, okay? That's something we call strength. So when I apply a load, I call it stress. So when I apply a load, this is what we call stress. The capacity of an object, of a skin, of a body, of a column, we call it strength. they are both have the same units, which is force over inch square. But when I say the capacity of the skin, in order to pierce a human skin, you need 100 pounds per inch square. This is your limits, above which a skin gonna fail. So that's why the shoe, which is 8.6 inches square, is safe for your hand, unlike a heel. Okay? So now you see that if we wanna measure intensity, it's incomplete to say, okay, I have a force of 200 pounds. You need to tell me this 200 pounds is distributed over what area? You need to describe the area as well so that the whole sentence is complete. So some might ask me, what is the difference now between pressure and stress? Both are force over area. But we use pressure when we speak about fluids. And we use stress when we speak about solids. They both are the same units, force over area, but one of them is for solids and the other one for fluids. So now we have two main types of stresses. We have something we call normal stress, which is in form of tension or compression, which if this is the cross section, this is the beam, and this is the cross section. And again, when I talk about cross section, as if I cut the beam and I left this to speak out the cross section. Normal stress is something that I either push or pull through the cross section. So normal stress is in form of tensile stress or compressive stress. When I push this cross section, I'm applying compressive stress. If I am pulling it, I am applying tensile stress. So normal stress is normal to the cross section. Okay? And we have something else called shear stress. And shear stress, it's not something perpendicular to the cross section. It is friction to the cross section. So if I'm applying a force, and instead of I'm pushing or pulling, my force is going to be parallel to the cross section, tangent to the area. So if my force is tangent to the area or parallel to the area, it's what we call shear stress. Okay? We have two different types of stresses now. We have normal, which is either tension or compression, and we have shear, which is in form of friction. Okay? So let's go into this a little bit further. So normal stress, the first stress we have is normal stress. Okay? And the symbol we use for normal stress is sigma, which is something like this. Okay? And again, all the stresses, normal or shear, they have the same equation, which is force over area. But what's the difference between normal and shear is what area to choose, and I will explain that in a moment. So for example, if I have a rope, which is this rope, and I apply the force of P, and if I took a cross section of that rope, I have something like this. I have three parts of it that contribute to the whole area. So I have each one has a diameter of 0.1. So the whole area gonna be 3 times pi d squared over 4, which is 3 times the area of one circle. Okay? And if I want to find the normal stress for that, I will say the force, which is this force, which is P, over this area. Okay? So I will say P over, for example, 3 pi 0.1 squared over 4. And the force, it comes in different units. It can either come with pounds, it can come with kilopounds, which is kips. And kilopounds is larger than pounds. So if you want to convert from kilopounds, which is kips, to pounds, you want to multiply by 1,000. Also, the force can come in terms of Newton and kilonewton. So always kilo is larger, kilonewton is always larger than Newton. So when you add kilo, that's 1,000 difference. So if I want to convert also from kilonewton to Newton, you need to multiply by 1,000. The area can come in like inches square, feet square, or meter square, or even millimeter square. That's the units. And then the stress itself, if you have pound and you have inches square, then you can have pound per inch square, or we call it PSI, which is pound square inches. If you have Newton over millimeter square, we call that megapascal. And if I have kip over inch square, we call it KSI, which is kips square inches. I would recommend, starting from today, to just, because the exam one and all the exam, it will be you will have a cheat sheet. And it's like one paper, face and back, and you need to write everything in those. So I would recommend you should start from today setting up your cheat sheet by writing, for example, the units and, for example, the stress equation until we reach. Okay, that's my dad. Omid. I don't know, Omid. Yeah, he's in a different country, so different time zones. Am I still connected? Okay. Anyway, I'll call him later. So we have kips inch square. 1 minute, let me check the phone because I think, no, it's on airplane mode. Never mind. Okay, so now I would recommend starting writing all these units in your cheat sheet at the beginning, so that when we arrive to like the week of the exam, you will have your cheat sheet ready. Okay? So you also have kip inch square, what I'm missing. If you have Newton meter square, that's Pascal. Okay? So now we all agree from like the first example that we said, that if I reduce the area and I have the same force, that will be larger intensity, right? So if I give you an example like this, I have a big circle and I have a small circle, and both of them has the same P, same force, different areas. Which one do you think is more critical to calculate? The stress in the small circle or the big circle? That's correct. So the stress in the small circle, if I told you what is like the maximum stress that's gonna happen, if both circles have the same P, you should always go with a small circle. You can calculate both of them and you can like conclude from the number that the smaller one will get you a higher stress, but also it will be very smart from you if you, at the beginning, to save time, you say, you know what, like I know the smaller circle will get me a higher stress. Similar with if I have a plate like this, and it has a hole in it, and I apply the force, which is P, okay? Which one do you think of those two you think the failure gonna happen? I mean, like, do you think if I pull the plate, the failure gonna happen here or there at the hole location? Hole. Anyone can tell me why? That's correct. Because I have here, if I cut the cross section, and this is the cross section that you will put in here. So you will take this P and put it there, and you will have this area, for example, and put it here. If you put both areas, you will find this one will give you a higher stress because it's a low, higher stress because it's low area. Tell me.
Is that only if the forces are where they're shown right there, or can the bigger cross section have a spot where if the forces are in this spot, it'll kind of go?
Oh no. What I'm saying is like the whole plate is subjected to the same P, constant force. I'm not changing the force. Later in the class, we will be changing the force. But if I have the same force and you get to have like different cross section, you can check both areas. But I want you to know before calculating that this one will give you higher stress. So whenever you see a hole in a plate, you need to focus on that cross section, which is this cross section will give you a higher stress. Okay? Any questions so far? All good? Okay. Next thing we call shear stress. So when we apply a force and we have this plate and we are applying a force, you all agree with me that this plate gonna feel normal stress. But in order let me take this one. So this is the 3D for that, and this is 2D. In order for this force to transmit, for example, to 1 minute. Let me erase this force and put a fixation here. Okay? In order that this force be transmitted to the fixation, this will be the load path, right? So the pin or the bolt gonna experience a shear. And let me show a video that explain this more. So same example. I have two plates. This one is fixed to a wall, and this one gonna be pulled down. I want you to see like the failure, how it's gonna happen. What do you think the bolt itself experienced? Did the bolt experience tension or compression, or experience some sort of friction? Shear. So the force was parallel to the bolt. So the bolt couldn't resist all this force. That's why it broke in a shear. It didn't break like this, or it didn't break in compression like it buckles. No, you saw it broke parallel to the cross section. That's what we call shear. And to prevent this kind of failure, which area should we like increase, for example? Should I increase the plate thickness or width, or should I increase the bolt area? What do you think? Bolt. Anyone say the plate? Or we all agree on the bolt? And that's right. Now, if I want to write the equation for the shear stress, we don't say tau, so we don't say sigma, we say tau. And this is for shear. And the same equation, it is force over area. But the thing is, which area? So the force is going to be the same. It is wrong that if you want to calculate a shear stress, that you will take, for example, the area of the plate. And instead, you should take the area of the pin or of the bolt, which is, if I gave you the diameter, a diameter of something, you would either say pi r squared or pi d squared over 4. Okay? Okay. Let's make it a little bit complicated by telling you this P gonna have one load path to go to the fixation, right? This is what we call single shear. Okay? But what if we have the force that went through two load paths? This is what we call double shear. And the equation is a little bit different. It's the same, tau equal force over area. But the thing is, will the cross section of the pin gonna experience the whole 80 kilonewton, or the 80 kilonewton be divided? The 80 kilonewton will be divided. So that's why I can say the equation now gonna be 80 over 2, which is P over 2, over the area of the pin, which is pi d squared over 4. This is one way to look at like single shear or double shear. Other way is how many planes of failure gonna happen. So here, for example, you all saw from the video that I have one plane of failure, which is the pin gonna break here. There is no other chances, right? So the equation, we can modify it by saying we can multiply m times area. And m here is the number of failure planes. Now, in the double shear, how many planes of failure do we have? We have, correct, we have 1 and we have 2. That's why we can say the same equation, 80, which is the whole force, over m, and m is 2 planes of failure, times pi d squared over 4, which is the same thing. Here I said p over 2, and here I took the whole p and divided by 2, which is the same thing. So you can look at the whole thing, either how many load paths do I have, or how many planes of failure do I have. Let me make it more complicated by saying if I have a plate here, and I have the other plates there, okay? Let me erase that one. How many planes of failure do I have? I have 1, I have 2, I have 3. So whatever force that's here, I will divide it by 3 times the area of the bolt. So I have here single shear, double shear, triple shear, and I can go all the way long. As long as you understand how many plane of failure then, or how many load paths do I have, then you can divide it by the force. Is that clear? Okay. I have, yeah, this was the failure, and this is the force that came, and that's how it's going to be distributed over the cross-section of the bolt. I have one more stress, which is not new. It should be covered under one of the 2 stresses that I mentioned, but I'll have you tell me which stress is this, either shear or normal. So imagine I have this plate, and I fixed this plate in the roof, and I put a rod in between, and this plate is like timber, for example, and I fix it up there, and I jumped and I hold it. And if I'm heavy enough, I'm going to take this rod with me down, right? So what do you think that this rod, like what kind of stress that this rod doing on the plate? Is it normal or shear? I'm not saying what is the rod feeling. I'm saying what the plate itself feeling. Normal. Anyone would say shear? No. That's right. The plate itself feels normal stress. And bearing, this is what we call bearing stress. And bearing stress is falling under the umbrella of normal stress. So we have normal stress that goes on, like we have normal stress, then under the normal stress we have tensile stress, compressive stress, and bearing stress. But the question here is going to be, what area should I choose? So previously, when we apply the force like this, we are exaggerating when we say the force is applied to this point. And instead, what we do in real life, we put like a thick plate here, and we apply this force on that plate so that the force will be distributed over the whole cross-section. So when you see something like this, it doesn't mean that there is a point load. No. We put like a plate so that we can have this force distributed over the whole thing. Or if we have the force being applied in a single load, which is unlikely to happen, at the beginning, yeah, it's going to be point stress, and then it's going to be something like this. And then starting from here, it's going to feel like the whole section going to work. Do you imagine this? When I apply a point load, but forget about this. This is like something extra. But whenever I show you P, you should expect that I'm putting like some sort of plate that will distribute the load from the very first point. In real life, if you see someone putting point load, it will take time until the whole section gonna feel the point load. At least in the beginning here, small area gonna work, and it's gonna expand until like the whole cross section gonna work. I'm explaining to you how the point load works, but in this class we're not interested in point loads. We're more interested in how, in this load gonna be distributed over the whole area. So now we said that this load in the normal stress is distributed over the whole area. What about this? What area is my load is supported by the whole cross section or in the contact of the rod with the plate? What do you think? Okay, if you're still confused, let me show you how it's gonna fail so that you would understand like how it's gonna behave. So this was the failure of this. So which area supported the rod? Is it like the whole plate or the interaction of the plate with the rod? Sorry, interaction of the rod with the plate. The interaction. And it's very small that this area, for example, before it broke like this, the area, if I had a rod here, this is the area, for example, that was pressing, but from the other side. Let me, yeah, this was the photo before it broke. So the rod was here. So the area that, if I'm pulling the rod this way, the area that's gonna work is starting from here, right? Which is something like this, which was the cross section here. Which is in other like words, something like that. Do you agree that this is the area that resisted the rod? And if we want the plate to not fail, we can increase, for example, the thickness of that area, right? And that's when the rod can resist my weight and like not fall with me. So if I have, let me see if I have this. The bearing stress, which is sigma because it's normal, again, it's gonna be force over area. So, okay, we know the force, which is my weight. What area should I choose? Yeah, you can throw any guess. Okay, half circle area. What anyone thinks?
It's like half the surface area of the cylinder, like just the body.
Okay, that's correct. Times the thickness. Correct, times the thickness. Okay. So you would all say that this is the area that resists. And the area gonna be like, for example, the diameter of the rod, for example, that was here, right? Times the thickness. We said diameter because this is, right? And the thing is, someone might say, why don't I take this area, which is half the circumference area, right? If, look at the failure. Because the failure itself wasn't constant in terms of, you will find that the sides felt zero stresses and the stresses peaked in the middle. So this wasn't a uniform stress. It wasn't constant. I would agree with you to take the circumference area if the stresses was something like this. It was like, not like this. If the stresses was, what's going on? Was uniform. But if I am to draw the stresses, it's gonna be something like that. So at the sides, it's zero, and it's picking up until the middle, and the middle is peak. So because we don't have a uniform stress and it's not constant, we instead gonna take some sort of like the average of this. And it's pretty accurate though. It's not like what we are underestimating the force. And there is like another derivation. I mean, I chose this explanation, and there is another explanation for that, which include the integration and derivation. But I'd rather to go with this, which instead of taking the circumference area, I would rather to take, oh, I don't have it here. Okay. I will take this area. Okay? I don't want to take the circumference because the circumference area, if I compared, so the circle is 2 pi r, which is the whole circumference, and if I divide it by 2 for the half circumference, I will have pi r. But if I would take the rectangle, which is the diameter times the thickness, I will have d times t. And d times t actually is smaller than pi times r. Okay? So now I have a very close approximation of the non-uniform like load or stresses, and actually we're not underestimating anything. We are getting like a smaller area than the half the circumference. So whenever you see a bearing, you would always want to take this area. That is the contact of the projected contact of the rod with the plate, which is the diameter of the rod. If I have a rod here, the diameter of the rod times the thickness of the plate. And this will be my area. So if I want to say, okay, what is the area and the bearing stress, I will say the force times the diameter of the rod times the thickness of the plate, which is basically this area. And again, I'm not taking any circumference because the distribution of the stress wasn't, as you see from the failure, wasn't constant. It peaked in the middle. So that's why I took a rectangle, like a projected area. Okay? Any questions? So now, if I have one hole, so the force is gonna be P times D times T, P over F over D times T. But if I have two holes, so the force gonna be distributed over two. So each area gonna feel, so I will say F over 2 times dt. Because the dt here, the dt, which is this area, not gonna feel the whole force. It's gonna be divided to 2, right? And the same thing if I give you like 4 holes, the force is gonna be divided to 4. Because dt is this area. And this area is subjected to F over 2. It's not subjected to the whole F, because whole F, again, is passed through both of them. Is that clear? Any questions? All good? I forgot to bring something, but there is something else we call torsion, which I will explain more next. But it is something like this. If I apply torsion, imagine that this is one piece. And I hold it like this, and I rotate it until it broke. What kind of stresses you think this is? Normal or shear? If I have some, you know the rectangle tube that I brought last time? If I rotate it, or if you have, for example, a gum, and you rotate it all the way until it broke, what kind of stresses this is? Is it normal or shear? Shear. Why is that? And the twist is parallel to the cross section. Yeah. That's right. Okay. Yeah, which is this. I was looking for this. So this is the rod, which is D is the diameter, and T is the thickness. So this is the projected area that can resist the bearing. So if I want to prevent the bearing, I either increase the diameter, or increase the thickness, or increase both. That's how that's how I resist the bearing. Okay? You always look at the equation of the stress. Stress, or even the shear, it is force over area. So the stress is directly proportional to the force, and the stress is inversely proportional to the area. So if I want to reduce the stress, I need to increase the area, which makes sense. If I want to resist more loads, I want to have big diameter, or like big area. Okay? Last thing here, I want to talk about factor of safety. Okay? And factor of safety, the equation for that is capacity, bless you, over demand. What does that mean? That means, let's go back, okay, let's finish this and we go back to the beginning. So capacity of demand, the body to be safe, or the member to be safe, the factor of safety need to be greater than 1. Okay? And I want to put equal here, but like we don't usually make it equal. But let's say, like theoretically, the body to be safe, you need to be greater than or equal 1. Let's go back to this problem that we had here at the beginning. We applied a stress of 1600. So the factor of safety for the skin, the capacity of the skin was 100, right? So if I say 100, that's the capacity. The demand is what stress I'm putting on the skin, which is 1600. Right? So is this going to be greater than or equal 1, or even less? It is 0.06, which is less than 1. That's why the skin going to fail. So if you have a factor of safety is less than 1, then it's going to fail. Okay, What about the shoe thing? So if I have factor of safety, I would say the capacity was 100 of the skin, and the demand, which is the stress I'm putting on the skin, is 8.6. So the factor of safety is what? It was 11.6, so I'm greater than 1. So I'm 11 times safe of breaking the skin. And that's how we design building, for example. This hall, for example, takes 100 students. But we don't design these slabs and these columns on 100 students. We design it on like maybe 2 or 300. And when I say 2 and 300, it means factor of safety from 2 to 3, in case that there is like a protest here, in case of anything accidental happen. Same as bridges, for example. We don't design bridges on cars. We design bridges, for example, on tanks, because in case any war happen, we should, like, the bridge should sustain tanks. So here there is like a high factor of safety. Nuclear plants, we like, I think, I'm not expert in that, but like we might put a factor of safety of like 10 or 11, because like a very small unaccidental loads can happen, can blow everything, so that we are designing on the accidental loads that might happen. Each case has its own factor of safety. So this is the whole story about factor of safety. So sometimes I might ask you, I don't know if it's in the in-class assignment or in the homework, I'll ask you, okay, what is the diameter to resist this force, for example? So what would you say? I will give you the strength of the diameter, for example. I will give it to you, and you have the force, and the unknown will be the D. So you can simply calculate D that will resist this force. But this is barely resisting the force. And I will then tell you, okay, what is the diameter now when a factor of safety is 2? So you will simply take the diameter that you got that will barely resist this load and multiply by 2. So you wanna increase the diameter. Is that clear? Like the factor of safety thing? Okay. We have a last example that will summarize everything. So what we discussed today, we can check the safety of this part. This part has a force, okay, and has a plate, and has like a bolt. So I would ask you, check the safety of this whole thing. So, and I will explicitly tell you what to check, but like in this class or in this lecture, what we learned, we can make sure that this P doesn't break the plate or doesn't break the bolt. In 3 checks, we will check the normal stress on the plate, the bearing stress on the plate, the shear stress on the what? Bolt. Take care of the wording. I will not ask you shear stress on the plate. The shear stress on the bolt. So that it's like also like I'm giving you a hint that the area that you want to take is for the bolt. Sometimes, like like later this semester, we will show you like when to take the shear for the plate. But in this case, this force is gonna exert or like gonna do like shear on the bolt. This example, for example, this is a 3D of a plate that is hanging by these 2 plates, and there is a bolt in between, and the diameter of this bolt is 0.9. This is, I think, the last time you will see the 3D of this, because usually we give you the 2D of that. You guys took engineering drawing? I don't know if this class is here. Like you take like 3D, then 2D, then elevation, then... Anyway, but you all agree with me that this is the 3D, and if I'm looking from this side, this is the 2D for this. Okay, you all agree with me. Because, for example, in the in-class assignment, starting from now on, you're gonna see something like that. There's no 3D anymore. So this is a plate, and this is the other 2 plates, and this is the pin. And the question asks you, calculate the maximum normal stress in plate 1, which is this plate, calculate the maximum shear stress on the pins, which is this guy, and calculate the maximum bearing stress on the plate. Okay? And check the safety. Check the safety means like calculate the factor of safety, for example. Okay, let me write that down. Okay, if I said check the safety, compare it with the strength here, and tell me if it's safe or not safe. I need to add something and calculate FOS, which is factor of safety. Okay? So let's start with the beginning, which is I want to calculate the normal stress. I don't have the answers for that, so I need some calculators here. Okay? So the normal stress on the plate, I will say I have two cross sections that I want to check the normal stress against. I will take this cross section, and for the pen, in order to put a pen, I need to have a hole. Okay? So I have a two cross section area that I need to check. This guy, which is 10 times 2, which is this. And I want to check another one, which is this one. Where is this section? At which location? At here, right? At this section. So I have two sections to check. This is 2 inch. The whole thing is 10 inches. And then this is the diameter of the pen, which is 0.9 inches. Okay? Do I need to calculate both, or some of you might expect one of them will give me higher stress? Do you all agree with him? Okay. So normal stress is force over area. And all the stresses we have here is force over area. Remember that. So the force is 14 kips, and kips is kilopounds, over the area, which is 10 times 2 minus 0.9 times 2. Ten minus 2, like the whole thing, I'm subtracting from it 0.9, which is diameter, times 2, which is the thickness. You all following? Any questions? Okay, what's the answer for this? Anyone? Anyone agrees with him? Okay, 0.79, 0.77. What's the units here? I have kips in the bottom, and I have area, which is inches squared in the bottom. Top kips and bottom inch square. So what's the units? KSI. Or someone might write kips over inches square. Okay? I want to check the safety. So I will look at the strength, which is in form of allowable. So allowable means accepted for the plate. So what's accepted is 1 KSI. Am I safe or am I unsafe? I safe because I am less than 1, because 1 is the 1 KSI here. So allowable means you are only allowed until 1 KSI, above which it's gonna fail. So okay, now I'm safe in normal stress. Should I leave the question and go to the other one? No. You need to check the whole thing, and that's what happened in real life. You need to do a lot of checks, and design is nothing but checking all the stresses or like all the safety concerns. But I want to also calculate the factor of safety here. Like, am I safe by what? By how much? So the capacity is what? Anyone? Okay, the capacity is 1, because that's what's allowable here. The normal stress allowable for the plate is 1 KSI. So I'll put 1 at the top. What is the demand? What I'm demanding here? 0.7. So I'm safe by how much? 1.29. As long as it's greater than 1, then I'm fine. I'm happy. Okay? Okay, let's check another thing, which is bearing stress, which is like sigma bearing allowable for the plate is 20 KSI. So I will say the bearing stress, and I will say, you can write here that this is normal and this is bearing. I would say force over area. What force should I take? same, which is 14, right? So I will write 14 kips. And now the tricky part, what area should I take? .9 times thickness. Do I get a second on that? Anyone disagrees with that? Okay, so the area here gonna be 0.9 times the thickness, which is what? 2 inches. Okay? What is the stress here? I'm getting 7.7 KSI. Am I safe or unsafe?
Yes.
I'm safe. So you can write safe. And you can like do your own signature. I used to do this when I was a student. I used to make like this, as if I designed this. Okay, and I'm safe by how much? Capacity. My capacity was what? 20, right? So the capacity is 20. Demand is 7.7. So I'm safe by how much? By 2.5. Greater than 1, I'm happy, you happy. Okay? Last thing is shear stress. I have 1 minute, so I need to write that quickly. Okay, shear stress. Tau, force over area. What force should I take? 14. Okay, tricky part. Is it single shear or double shear? Double shear. So I either divide the force by 2 or write it 2 here as if like it's a plane of failure. And whoever said double, the reason why is there is 2 chances here that the bolt kind of fail, or I do have 2 load paths here. That's why I'm dividing the force by 2, because the area of the bolt here is experiencing F over 2. Okay, so 2 times what? Pi d squared over 4, which is over 4. What is the area? What is the stress? I got 11 KSI. Okay? 11. And what's the allowable? 14. I'm safe or unsafe? Safe. So you can write safe in green and make your signature, and then FOS. Capacity. What's my capacity here? 14. What's my demand? 11. So I'm safe by 1.27. As long as it's greater than 1, I'm happy and you are happy, right? And that's all. So since I finished the lecture now, like on time, that's cool. I will upload this right away so that you can have it under module 1. And I will see you all in class assignment tomorrow in session.